Okay. So good afternoon all. So today we will continue with the remaining part of GD&T characteristics. So just we will revise all the things regarding GD&T quickly. I will share my screen with you. Okay. Right. So yesterday we have seen these four characteristics like straightness, flatness, circularity, and cylindricity, right? So geometric characteristics. So there are 14 characteristics, and out of them, we have seen straightness, flatness, circularity, and cylindricity. All these four characteristics are form type of characteristics, and they doesn't depend on any other feature of a component. They don't depend on any other feature of a component. Okay, so they are self-dependent, means they are a form type of characters. So we are talking about forms of that particular feature of a component. Okay, so straightness applicable for very short width components, long components, and for cylindrical components. So for proper smooth performance of a particular component, we need that part to be straight. Flatness is applicable for components having surface having good proportion of length and width. Okay, so there we need to maintain a flatness, and that should be within permissible deviation specified by the feature control plane. Similarly, circularity. Circularity is again applied for thin rings or for cylindrical components having very short functional way. There we apply circularity, or we apply circularity for conical components also. Means we just measure circularity at particular section for conical components. One more thing is we can apply circularity for profiled components. Means circular component is there, but its diameter is varying. Okay, so for profile components also we can apply circularity. Cylindricity is applicable only for cylindrical components, not for conical components. Means that maybe the question in interview. So in cylindricity, circularity plus straightness means it's a combination of these two characteristics, circularity plus straightness. So when we measure circularity along the length, then it is cylindricity. But we have to consider all the readings, not readings at the particular section. Okay. So as I said, these all are form type of characteristics. Now we are moving towards next three characteristics, next group you can say. So here these are the first three characteristics like parallelism, perpendicularity, and angularity. Regarding position, already we have seen that while going through some case study I have shown you regarding covering clip. So position we have covered already, means what is difference between traditional tolerancing system and geometrical tolerancing system. So we discussed the position of a hole actually. So today we will try to finish these orientation type of characteristics like parallelism, perpendicularity, and angularity. So here these are orientation type of characteristics. Here we will talk about orientation of some feature with respect to other one. Okay. So again, this is common for all the characteristics. We are means we can apply GD&T characteristics when there is a requirement in assembly. Means any other part is to be fitted on the feature under consideration. Means it is applicable for assemblies. When there is a one-to-one fitment, then we apply GD&T. case. This is parallelism. Again, we will go by same way, like what is applicability, where to apply these characteristics, then feature control frame, then its explanation, means what is meaning of that feature control frame, and what are the different inspection methods available to check parallelism, and whatever characteristics we will see. So again, you can see here machine made. Okay, so here you can find different T slots to hold the fixture assemblies on this component, or there are slide ways, or you can say guide ways. Means this complete table is moving. So in this direction also it can move, or in this direction this table can move. So there are some guideways. Okay, so for smooth motion of this component, these guideways surfaces should be parallel to each other. Okay, so here you can find guideways, or here you can find guideways. So these guideways should be parallel to each other. Actually, these guideways, so here you can see if it is a vertical guideway, means complete vertical face is there. This face and this face should be parallel. Now here, if you see it properly, this is dotted type, so angular type of guideway. So for angular type of guideways, we cannot apply parallelism, but if it is, in some cases, these guideways or guide surfaces are parallel to each other, vertical or horizontal. So any can be the orientation of surfaces, but both should be parallel to each other. In that case, we can apply parallelism. Or a simple example you can take is a drawer of your table. So table can be of wooden or of metal, but you can think of a drawer of wooden table. So opposite faces of the drawer or the cavity inside the table, so opposite faces of that cavity, they should be parallel to each other. Okay. So I'm not talking about surface of drawer and surface of that cavity. So you can apply parallelism between same component. Means two opposite faces, two sliding faces of drawer, or two faces of opposite faces of cavity. They should be parallel. Okay. If there is error in parallel, one surface is not parallel to other, then we cannot move that drawer properly or smoothly. Okay, so the drawer motion will not be smooth. Means I think you might have experienced it in rainy seasons. So in rainy seasons, that plywood or wooden material get some bumps on it due to moisture content in the atmosphere. So that loses its parallelism. Means the surface not remains parallel. So we feel that difficulty while pushing and pulling that drawer, right? So for smooth motion, these guideways or slideways should be parallel to each other. Okay, so in number of machines you can find parallel surfaces, and we are expecting parallelism between these two surfaces. Means surfaces should be from same component. Okay, so you can find it in lathe machine also. In lathe machine bed, there are two surfaces, they should be parallel. Okay, slide surfaces, slide ways means that saddle, or you can say what it is called, where the date center is mounted. That complete assembly moves on the slide ways of lathe machine. Okay, so these ways, slide ways or slide ways, should be parallel to each other. So we can see applicability means what are the examples and how the parallelism is applicable for different components. While considering parallelism, we can apply two cases. We can discuss two cases. One is parallelism between two surfaces. Like I told you, two guide surfaces or slide surfaces of some machine made. So there are two surfaces, and we are expecting parallelism of these two surfaces within some allowable limit or within some permissible deviation. So parallelism between two surfaces. So this is the case where we are expecting parallelism. So if you know this component, these are simple plates. Okay, and these are called as fixture plates, means used for fixtures, fixture assemblies. So on these plates, complete fixture is assembled and used, and this fixture assembly is fitted on a machine bed. So bottom surface of this fixture plate will be rested on machine bed, and on top surface we will mount different components. So arrangement to hold the workpiece to be machined. So this is arrangement to hold the workpiece. So to have this proper machining operation means that operation or that feature to be machined should be accurate. So we need these two surfaces, bottom surface and top surface of fixture plate should be parallel to each other. Here also you can see this different type of slots are there to accommodate fixture assembly. You can fit different components on these surfaces using bolts, pins, or some tightening clamping devices. Okay, so there are slots, there are some elongated holes, there are some circular holes. Using this, we hold different components on these fixture plates. Okay, so there should be proper orientation. Okay, so that same surface orientation should be passed to the workpiece also, so that there is no error in a feature to be machined. So for that purpose, we need these surfaces to be parallel. One more example is bench wise. I think you might have worked on this with this assembly in your first year fitting practicals. Okay, so here we use this bench wise to hold the component. In these jaws, we hold the component. We tighten this screw to hold the component, and then we can apply some operations on the components. So here you can see these slide ways. So this is moving jaw or a sliding jaw, and this one is a stationary fixed with the table. This jaw is a stationary one, and it is fixed with the table. And this one is a sliding. With the help of this screw, we can move this jaw, moving jaw, okay, in this direction. So here you can see these two surfaces. This is one surface, and one more surface is on the opposite side. So we can expect parallelism between these two surfaces, right? So these two surfaces should be parallel to each other. If there is an error in parallelism, if these two surfaces are having some inclination, then it is difficult to move this sliding jaw. Okay, so you might have experienced that. After sometimes there is a possibility that this guide may get uh, some rusting process. So there will be some error, surface error, or it may get changed due to wearing action is there. So due to that, it may lose its parallelism, and we can face difficulty in sliding motion. Now, one more case for parallelism is parallelism between two axes. Okay, so if we need two axes parallel to each other of different components, then we apply this condition, this case. So here this one is press tool assembly. This type of tools are used for press work or punching operations. So if you want to punch some holes, okay, so holes can be created by punching operations also. You can drill a hole using drilling operation. If you want to create a hole in sheets, generally we use punching operation. Okay, you might be known this punching operation. So punching operation is used to create holes in sheets. So these are the this is the punching tool, or you can say punch and die. Okay, so using this punch and die assembly, we can create holes. So for proper punching action or operation, punch and die should be aligned properly. Means if punch and die is having offset or somewhat means their axis is not aligned properly, then that shape of punched hole will be of having some error. Means it will not have pure circle shape. So to ensure alignment of punch and die cavity. So here there will be die, and here there will be punch mounted on this upper plate. So alignment of punch and die is very important. Okay. So for that purpose, there are some bushes and guide pillars mounted on the bushes mounted on this upper plate, moving plate, and this one is a stationary plate, and these guide pillars are mounted on this stationary plate or where there is a die. Okay, so when this upper plate comes down for the punching action, these guide pillars will get inserted inside the bush. Okay, so before that punch comes in contact with the workpiece, these guide pillars get aligned with the bush, ensuring perfect alignment of punch and die. So, due to these guide pillars, alignment of punch and die will be ensured. So, these guide pillars, I think on this plate there are four guide pillars and four bushes. So these guide pillars will get inserted in the bush. These guide pillars should be parallel to each other. Axis of these guide pillars should be parallel to each other. So here we can, this condition or this case is applicable. We are expecting parallelism between these two guide pillars, axis of these two guide pillars, or these holes means axis of these holes should be parallel again. Okay, so this is the case where we can expect parallelism between two axes. Okay, so these are the two different examples for parallelism between two surfaces and parallelism between two axes. Now, how to draw a feature control frame? And a feature control frame requires symbol, that characteristic symbol. So for parallelism, this is the symbol. You can see it on the screen. Two parallel lines having 60-degree angle. Okay. So this is the symbol for parallelism, and it is placed in a first chamber of feature control frame. So first we will consider parallelism between two surfaces. Two surfaces must be parallel within the specified limit. Now here, first time we are going for a characteristic or orientation type of characteristic. Here it is dependent on any other feature of a component. We have seen straightness, flatness, circularity, cylindricity. There, these were form type of characteristics. They don't require datum or they don't require any reference. But here, these are the orientation type of characteristics requires a datum. It means that there will be third chamber in a feature control frame. Okay, indicating a datum, indicating a reference. So here, parallelism is with respect to any other feature. You can see here, there is a surface B. Now this is side view, this is front view, or you can call this as a front view, this as a side view, anything. It is okay. So this top surface is surface B and this bottom surface is surface A. Again, these are labels. This surface is labeled as B and this surface is labeled as A. Now, we are expecting parallelism between these two surfaces. So here, feature control frame is attached with this top surface B, right? Means what? We are expecting parallelism of this surface with respect to this. Means this surface is a feature under consideration and this is a datum feature. Okay. Now it is in drawing. This line is a datum. It is not a datum feature here. Here we are talking about line. Datum is a virtual one, imaginary one. And datum feature means the physical surface available in the component. So this is a table of any, suppose, milling machine. So these are the T slots available on the table and this one is the bottom surface. Okay. So we are expecting this surface to be parallel with this. So here this sequence is important now because in last four characteristics they were form type of independent characteristics. Here it is not like that. Here we are talking about parallelism. So The language is important again because here this surface should be parallel with this. Okay, so feature under consideration should be parallel with this. You can consider any surface as a datum surface or any surface as a feature under consideration, but that depends on functionality, or that depends on manufacturing capabilities, that depends on inspection process, means which is convenient for manufacturing engineer, which is convenient for inspection engineer. That surface is generally considered as a datum. Means inspection process, manufacturing process should be convenient. So that surface we will consider as a datum surface. Okay. So here it is a datum surface, datum feature, or in drawing it is called as a datum. With respect to this, we are talking about parallelism of this surface. So feature control frame is attached with this. First chamber indicates parallelism symbol. Second chamber indicates permissible deviation, or you can say maximum permissible deviation. So here this surface is allowed to deviate between parallel planes separated by 0.2 mm, 0.2 mm, 200 microns. Again, third chamber indicates datum or a reference feature. So here A, so the surface which is labeled as A is a datum feature for this surface, right? So here it is labeled as A, and it is considered as datum here. This surface, or you can say parallelism of surface B, and that parallelism should be within limit of 0.2 mm, or maximum permissible deviation is 0.2 mm and here we are talking about parallelism of this surface with respect to bottom surface. So what happens while explaining this feature control frame, people explain like A is a datum surface, but you should identify that A surface, means you have to locate that A surface. What is A? Every time it is not surface, but for different characteristics, datum is different. Sometimes axis is also datum. So you should tell, or you should identify that feature. You have to tell about that feature, not like A is a datum, primary datum, B is a secondary datum, C is a tertiary datum. Don't read letters only. Okay, anybody can read letters A, B, C, D. It's not difficult to read these letters, but you have to identify what is A, what is B, what is C. Okay, so you have to locate that feature in a component. So BA is bottom surface right now here. So you have to tell about that bottom surface. B is top surface, or B is a feature under consideration. So you have to tell about this surface, not surface B, surface A, not like that. Okay, so here this of the table is again 300, 300, and tolerance is also specified plus minus zero point 0.5 mm. Again, you can see this is a bilateral tolerance. Okay, means this is a general purpose dimension. Okay, and here this is permissible deviation allowed for the parallelism of this feature. So always this value, permissible deviation value, is smaller than the size tolerance. You see, this is the size tolerance, height. Here it is talking about height of this component, and here we are talking about deviation of this top surface. Okay, so this may have deviation like up and downs on this surface, and this should be controlled within 0.2 mm, right? So if this value is having means this value is more than this, then it will be difficult. Means here what is the range? Means considering this tolerance, range of the dimension is 299.95, right? 299.5 and 300.5. So if you add and subtract this tolerance value from this dimension, you will get 299.5 and 300.5. So within that range, any dimension is acceptable, right? And if this value, which is defined in a feature control frame, it is more than this, so it's not possible. Means this cannot be more than this. If this component, here we are expecting 0.5 mm tolerance, and here if it is more than that, then it will be difficult. We cannot have deviation more than this size tolerance. Okay. So just remember, this permissible deviation should not be more than size tolerance, means not more than zero point 0.5. So here the difference means already we have discussed that datum point means as this is an orientation type of characteristic. Now there is a change in feature control frame, and that is there is a third chamber indicating datum. Okay. Now explanation means what this feature control frame means we are expecting some parallelism of some feature with respect to any other feature within the limit. So it is similar to flatness, means initially it is similar, looks like flatness, but here we are considering datum, means with respect to this surface we are expecting this surface to be in some limit, right? For flatness it is applicable for this surface only, up and downs of this surface, but here we are talking about orientation also. So we are talking about parallelism. This surface has to be parallel with this. So we have to mount this surface on surface plates. Surface plates means whose flatness is ideal. Ideal means not 100% flat, but 80-90% flat surfaces are available in inspection room. So we have to mount this component on the surface plate also only. And then we can check parallelism of this surface. We can check up and downs of this surface. So similar to flatness, we can check it with the dial gauge. So dial gauge pointer is aligned with this surface, and just you have to move this component, or you can move this dial gauge stand also. It will give you different readings at the different locations. So difference between higher point and lower point, okay, should not be more than zero point 0.2 mm, or the plane passing to higher point and plane passing to lowermost point should be zero point 0.2 mm apart, or these planes should be parallel to datum. Here the condition is, last time what happens means when we are discussing flatness, we said that these planes should be parallel to each other. Means planes which are containing this surface should be parallel to each other, whatever may be the orientation. We were not talking about orientation of that surface. Okay, in case of flatness, we were not talking about orientation of this surface, whatever the orientation is, but this waviness or unevenness of a surface should lie within two planes separated by some amount or the amount specified in feature control frame. But here, what we are expecting, these planes should be parallel to the datum. Okay, if this datum has some angle, then these planes will be parallel to that also. We are not expecting this horizontal or having some specific angle. Okay, so here it should be parallel to the datum. So here there is a role of datum feature. Or here what you can see is this is datum feature, means bottom surface of this component is datum feature. But sometimes these datum features are also not completely flat, or uh, flatness error might be there. Okay, so what we have to do is we have to mount this on a surface plate, means surface plate is now a datum feature simulator. You might have remembered that what is datum, datum feature and datum feature simulator, right? So what is datum? Datum is an imaginary term which is represented in drawing. So if you see this drawing, this is a datum because this is specified in a drawing. But actual part, actual surface of this component is a datum feature. And at the time of inspection, we have to mount this datum feature on some surface plate, okay, while measuring parallelism. So this surface plate is called as datum feature simulator. Okay, so on which this component is rested. Okay, so this is called as datum feature simulator. So here datum is important. That makes it different than the flatness. Okay, so what is explanation? We have discussed it in short. But just similar to flatness, here we will mount higher point and lower point from different orientations. So here this is suppose this is side view and this is front view. So we will mark orientation. What is the orientation of this surface? Okay. So here we have marked A point AA. This is in this orientation. This is AA line or AA means this is just for just to indicate orientation of this surface. So in front view we can see this is the orientation of this surface, and in side view this one is the orientation. Okay, so higher point might be in front view or side view, any view. So we have to locate that high points and low points, measure the heights with respect to the atom, and difference between high point and low point should not be more than the permissible deviation, right? So uh, this explanation is quite similar to flatness, but it is with respect to datum. This is the only difference. Here you can see this datum feature simulator. This is the surface plate on which this component is mounted. Okay. Now, how to check this parallelism for two surfaces? So we can mount this component on surface plate, and using dial gauge, just move this dial gauge on entire surface. You can have maximum deviation and minimum deviation. Difference between these two deviations is called as error in parallelism. If it is more than the value in specified in feature control frame, then the component is rejected. So this is the exact snap you can see. So he is measuring why it is not staying. Okay, so you can have a look. Uh, so he is checking some parallelism of a component. Okay. Then one more important point to note in parallelism is how to decide a datum. So we have discussed now. Here we have to talk in particular sequence, means one surface is to be parallel with the other. Okay, so while defining this parallelism requirement, we have to mention that sequence also. So datum, just a minute, I will just check this slide. Okay, so generally larger surfaces are preferred as a datum. Okay, so if you consider this component, this is the large surface. So we can mount this component on large surface, means it is aligned with the datum feature simulator, and parallelism is checked of this surface with respect to this one. So it's not a thumb rule actually; it's a guideline. Not always it is true. Means every time it's not like that. The large surface will be the datum, but it depends on convenience of manufacturing engineer, convenience of inspection. Means designer has to think in all point of view. Means how it will be convenient to manufacture. Means when we are expecting this surface as a datum feature and this surface as a feature under consideration, means at the time of manufacturing also we have to hold these components in the same way. Means this is to be aligned with the datum feature simulator. Okay, and then this is with respect to this is machine, means whatever operations or milling operation should will be there, suppose. So this will be with respect to this surface, means we have to hold this component with this surface. Means while machining, you cannot hold it in vertical direction and facing operation of this surface. It's not like that. Means you have to put this surface on surface plate, or you have to put this surface on a fixture plate, and then go for machining or milling operation of this surface. Because here this is the feature under consideration. Means while talking like uh, here, this surface is to be parallel with this one. Okay. If this is feature under consideration and this is datum, then surface A will be parallel to surface B, right? So this sequence is important. Generally, large surfaces are considered as a datum surfaces. Sometimes some components are like this. When two surfaces are preferred to be considered as a datum, okay, and smaller one is a feature under control. Means consider this type of component. So here we are expecting parallelism of this surface with respect to these two surfaces. Now there are two surfaces to be considered as a datum. Okay, and this is the feature under consideration. These are the datum features. But while defining parallelism, it's not like that. You have to define two datums. Means for orientation type of characteristics, there is no primary datum and secondary datum. So only primary datum, only third chamber will be there, right? So we have to define the atoms in third chamber. But here there are two surfaces. Simultaneously, we are expecting a parallelism of this surface with these two surfaces. So here this is called as compound atom. Here these are not separate atoms. Okay. So here the feature control frame will be like this. Okay. Right. So here in third chamber only, we will define both these datums. So this one is datum A, datum B. Sorry, I told you about these surfaces, but here we have considered these two surfaces as a datum surfaces. Not a major issue. So this is a first datum and second datum, but this is not a primary and second. It's not like that. This is primary datum and this one is secondary datum. Both are equally important. So we have to consider both these datums, but in a single chamber. Okay. So this is called as A dash B. It is written like A dash B, and this is called as compound datum. Okay. So we are expecting parallelism of surface C with respect to these two datums or these two features, these two surfaces A and B, bottom surfaces. Okay. So these are both equally important, and it is written like A dash B in third chamber, compound chamber. Now we come to parallelism between two axes, right? So already we have discussed about requirement or applicability. So same thing is shown here in this diagram. So you can see this is punch and die. This one is punch and this one is a die. And here there is a workpiece or component will be moved from this, and this is the punching action. This punch will come down, punch a hole here in the component, and this uh, cut material will be removed. But here what is important? Alignment of this axis. See, you can see this axis. So here this punch is moving up and down. Okay. So every time when it is coming down, there should not be any misalignment of this axis. Okay, it may happen. So if there is no guide pillars, so while coming down, it may get shifted. Okay, so definitely there will be error in a component or in a process. So this alignment should be ensured. So for that alignment, these are the guide pillars. So generally there are four guide pillars depending on size of this punch and die mechanism. So these are the four guide pillars, and while coming down, these guide pillars comes in contact with this bush inserted in the upper plate, moving plate. There are bushes fitted in the hole, okay, and they will have some interlocking kind of fitment, means they will not get removed with guide pillars. Means when it is going up in upward direction, bush will not get removed. So it will be fitted. It will remain here inside this plate. Okay. So first, these guide pillars will come in contact with this bush. They will get inserted inside this hole so that alignment will be maintained. Okay, if there is some shift, it will again due to this assembly or due to this action, this will be aligned again. This will get shifted and get aligned with the axis of die. So operation will be proper. Okay, it will create a proper hole. So to maintain that alignment, these guide pillars should be parallel to each other. Right? So these guide pillars, we are expecting parallelism between these axes of guide pillars. So this is actually a case where the case for the parallelism between axes. The same we have discussed right now. See here, you can see this. This is the punch and die. It is they are creating washers. Okay, there are two operations. So you can see this workpiece sheet. Okay. So here alignment is important and they are punching and creating washers. So one more example is molds. Molds used in plastic molding. Okay, injection molding tool. So here also, if this mold is not aligned properly, this one is cavity and this one is core and cavity. Okay, so it is a container type of component. You can see this from these two components. So complete mold is assembly of this one. Okay, this will be assembled and then with these openings, we inject molten plastic inside this cavity, and it is get filled after solidification. We will get the plastic component, desired plastic component. So again, alignment is important here. If these two molds at the time of assembly, means for ejecting the component, we have to disassemble this mold. Means these two parts will get separated. Core and cavity will get separated, and this component will be ejected. And generally, this will get separated, and this is the component remain in this will get separated by ejector pins. Okay, so after ejecting, again we have to these two parts are assembled and molten plastic is injected inside the cavity. So if alignment is not proper, we can get variable means different thicknesses on different sides. Means if this gets shifted on this side, left hand side, then here thickness of the compound will be small. Here we will get large extra material. So this variation in thickness of a plastic component leads to different cooling time. Means cooling time will be different for the plastic component after injection. Okay, or there will be mismatch, means there will be different error in a component also. So we have to ensure alignment of these two molds, and for that purpose these guide pillars should be parallel to each other. There are four guide pillars and they will get aligned with this guide bush. Okay, so this will get inserted in this, and these guide pillars and bush will ensure alignment of core and cavity. So we'll get a perfect product. Okay. So these are the different requirement or applicabilities for parallelism between two axes. Symbol is same. Only only one thing is changed here. So here there are two pillars or cylindrical features of a component, and we are expecting parallelism between these two components. Okay, and these two components are separated by 100 mm distance. Center distance is 100 mm. So the thing is, we will discuss first these features. So this is a cylindrical part of 30 mm diameter. F7 indicates fitment. Okay, so generally for shafts or for outer dimensions, we use small letters. Okay, and for holes it is capital letters. So here the fitment is 40 f7 and here it is 30 f7. 30 is a diameter nominal size of this cylinder or cylindrical feature. Here the diameter is 40. Okay, so what we are expecting, feature control frame is attached with the diameter. Okay, so for cylindrical components generally feature control frame is attached with the diameter value, diameter dimension. Same feature control frame is there, only change is zone descriptor. So here the zone descriptor is phi, means what, direction of deviation of this component is in circular direction. Okay, so we will check how it can be oriented, means, so this is feature under control, means we are expecting parallelism of this axis with respect to this, because feature control frame is attached with this. So this is feature under consideration and this is the reference feature or datum feature, right? So we are expecting parallelism of this axis with respect to this. So what is the possible error? So this axis may be deviated towards this, indicating this position N, or it may show this error, or it is shifted towards left hand side or showing the position M. So these are the possible orientations. Or if you see a side view, there also we can get a orientation error, means this axis will be oriented towards left hand right hand side. Okay, or around this axis it may get deviated, means in all directions. So if you see it in front view, we can have change in or error in orientation. In front view also, in side view also, in different angular views also we may have deviation of this axis. Means this axis will be tilted somewhat. Means it's not parallel to this axis properly. That tilt will be in any direction. Okay, around this ideal axis. So this is the ideal position. Okay, actual center. If you see this component from the top view, you will see only point if this axis is ideal. But again, we know nothing is ideal. So this cylindrical feature may have change in orientation or deviation in any direction around this axis. Okay, so if you see it in top from the top view, we may see a circle, small circle. Okay, so that axis should within that circle. The circular zone is there, or better to say there is cylinder. So if you see top view, you will see circle, but this is a cylindrical enclosure. Actually, you can say, means the axis should be enclosed inside the cylinder of zero point 0.2 diameter. Why 0.2? Because it is mentioned in a feature control frame, because it is the permissible deviation. So whatever be the error in this axis, it should lie within the cylinder of 0.2 mm diameter and height of that cylinder should be 50 mm, not more than 50 mm. Right? That's why it is a circular zone. So the axis is allowed to get deviated within the circular zone. Okay, that's why we have to write phi as a zone descriptor in a feature control frame. Now here it is the difference. Is in case of parallelism between surfaces, this is not applicable, but for parallelism between axes, okay, so with respect to this feature, it should be parallel. Then here we have to apply phi as a zone descriptor, right? How to do inspection? So yesterday also we have discussed about very cheap ways, cost point of view, cheap ways to for inspection, because inspection cost should be very low than the production cost. If the inspection cost is more than that production cost, so it is not recommended generally. Okay, so in for mass production, inspection cost should be too less than the production cost. Okay, so if you want to decrease or lower the production inspection cost, we should use some Uh, just a minute. We can use some qualifying gauges. So this one is a qualifying gauge. So uh, there are two circular cavities, or you can say holes on a component. Okay, so it is looking like a connecting rod, means having two holes at both ends, and here it is a facility to hold this gauge. So you can see our component is of this is the feature under consideration, and diameter of feature under consideration is 30 mm. Diameter of the reference feature is 40 mm. Okay, so while designing this qualifying gauge, means it will be different for different components. Means it's not like that we can use a same qualifying gauge for all the components. It depends on the workpiece or the component to be checked. I think this is different, means here the center distance is 150 mm and the diameter is 150 mm, but our component is of 40 mm. So here that diameter should be 40. Here feature under consideration is 30. It's correct. So we have to design a qualifying gauge for the particular component matching these hole sizes. So while inspecting, you have to just insert this qualifying gauge on the component and just check for the maximum contact. Okay, so if it is difficult to insert this qualifying gauge on a component, then understand that there is error. Means so here uh, that diameter will be this diameter will be more, or having some tilt, that much diameter is increased as per the requirements. Means here we are allowing error in parallelism is 0.2 mm. So that much space is available here. Okay, so that it can accommodate any errorless component. If there is error in parallelism in a component, the gauge should accommodate that component. Means if error is within the limit, then it should able to which we should able to insert this qualifying gauge. If it is more than zero point 0.2, then okay, then it should not enter in the hole which is available in qualifying gauge. Okay, so these are the simple qualifying gauge we can design for inspecting parallelism between two axes. This is one more method. So here we can have some sleeves mounted on a datum feature, and we can attach a dial gauge to this sleeve, and here we can have some arrangements to adjust the height. So along this length we can check different levels of this surface. So if there is any error in parallelism, we can get it in on a dial gauge indicator. Means on a dial gauge we can have that readings. So different, again, difference between maximum and minimum reading will be the error in parallelism. Okay. But here one thing is difficult, that if this feature under consideration is having tilt in this direction, okay, and it remains like vertical only. So in such cases, here it will not show any deviation, but actually the component is tilted in this direction. Okay, if the tilt is in towards this feature or away from this feature, then it's okay, we can mark that error. Okay, but if this component is shifted in this direction or having tilt in this direction, that error in parallelism, again, shift in this direction is an error in parallelism, because this will not be parallel to this axis. There is definitely error in parallelism. This axis is deviated in this direction, so we cannot get that error using this dial gauge arrangement. Okay, because we are checking in one direction only. If shift is in that plane, in this plane, tilt is in this plane, then only we can get that reading. So it's better. Again, this is quite costly as compared to qualifying gauge. this is quite costly and time consuming also, because one by one we have to check the component using dial gauge. So for each and every component we have to do this setup, having this height adjustment sleeves and lowering the height, taking different readings. So definitely it is time consuming. Instead of that, we can have this qualifying gauge. So you have to manufacture this qualifying gauge once, and you can use it for thousands of components. So a component costing around 100 or 150 rupees can be used for thousands of components. So that inspection cost will get divided. Okay, so it's very cheap cost wise, having qualifying gauges. Okay, so I will tell you one example. I think you might have known this. There is one industry in Mumbai. So they have all their quality inspecting inspectors, means quality inspecting persons, are blind. So you might be surprised, but all the quality inspecting persons are blind. So blind persons are checking quality of in components. So they have provided these qualifying gauges, and means if there is one sense is say is not up to the mark, means if they are blind, that sense is replaced by some other thing. Means they blind persons have good touch sense, so that person has used that quality of blind persons, and he has appointed all the blind persons as a quality inspector in his industry. So they have to just take the qualifying gauge, take the component and try to insert it. If it is fitting properly, they will judge it, uh, whether there is a perfect contact or not, and they can easily decide accepted component, rejected component. Okay. So qualifying gauge means, what I am trying to say is, qualifying gauge is very simple and very cheap solution. Okay. For mass production, this is definitely recommendable. So this is about parallelism, parallelism between two surfaces and parallelism between two axes. Now we'll go for perpendicularity. Is there any query? So we will have some 1 or 2 minutes break. So if you have query, you can ask me. Meanwhile, I will have some water.
Participants can ask your queries, if any.
Hello,
Yes, sir.
sir.
One question is there, sir. What is the meaning of bilateral tolerance?
Bilateral problem. Just a minute. Uh, I think here I have shown this bilateral tolerance in case of parallelism. So this one. So this tolerance, this dimension, 300 dimension, is having tolerance plus and minus. Okay, plus minus tolerance. Value is not important, but there is plus sign and minus sign also. Means what? The range of this dimension is from 299.5 to 300.5. Means when there is a plus and minus tolerance, it is called as bilateral tolerance, and bilateral tolerances are mentioned for general purpose dimensions. Okay, bilateral tolerances are mentioned for general purpose tolerances. And again, here we are talking about parallelism, and error in parallelism is considered by this tolerance also, means this geometrical tolerance also, geometrical deviation also. So this one is bilateral tolerance, generally not that much important, and it is converted into basic dimension. Okay, but just why it is shown here, uh, geometrical tolerance or permissible deviation should be less than dimensional tolerance. That's why I told you about this. Okay.
Is any other questions?
Okay, sir. We will move ahead.
Yes, sir.
Okay. So next orientation type of characteristic is perpendicularity. Parallelism, then perpendicularity. So perpendicularity also orientation type of characteristic. So we are talking about orientation of some feature with respect to other feature. Sometimes it is called as squareness also. So not many times you have seen checking squareness, right angles are generally checked. So in your home also you can check it. So while creating uh, door frames, carpenter, you might have observed that carpenter is making that door frame or any furniture item. All the times he will have that instrument. Okay, so checking right angle every time. So right angle is important definitely for all engineering, mechanical engineering compounds also. So I am telling you about general examples because you are just in your day-to-day life you are observing such components. Means if you see these door frames while manufacturing this, he is ensuring that perpendicularity of two arms, two vertical arms of door frame and one top horizontal arm of the door frame. So there he is checking perpendicularity. If that perpendicularity is not maintained, what will happen? Just think yourself. What will happen if that door frame or arms, vertical arms of door frame are not perpendicular to the horizontal arm? So at that time, no one will feel that there is some error or there is some problem. Okay, if that perpendicularity is not maintained at the time of manufacturing the frame, it is not a problem. But when we try to fit a door there, we are trying for fitting a door, then door will not fit properly. Okay, so for a fitting of door perfectly, we should fill all the gaps. If it is not perpendicular, we can adjust the shape of door, but there will be uneven gap between door and that door frame. So for fitting of door, perpendicularity should be maintained in a frame. So similarly for all geometrical characteristics, we are looking for assembly point of view. Any other component is expected to fit on the component. Okay, and we are expecting a proper surface to surface contact, maximum surface to surface contact. That's why these geometric characteristics are maintained. So for parallelism also, we are expecting some components to be fitted on these features, okay, on that surface. So we are expecting parallelism. Here also perpendicularity means we are expecting some component will come and get fitted in here at this angle, at this 90-degree angle. Okay, simultaneously expecting a good surface contact between these two surfaces and the concerned surfaces or respective surfaces of the other component. Okay, so simultaneously there should be proper contact between these surfaces. That's why perpendicularity or squareness is expected. So similar to parallelism, here also there are two cases: perpendicularity between two surfaces, perpendicularity between axis and the surface. Okay, so these are the two cases again for the perpendicularity: perpendicularity between two surfaces and perpendicularity between axis and the surface. So here with the one example only we can discuss both these applicabilities or both these requirements. So you can see perpendicularity between two surfaces. So here you can see this surface and this top surface of a cylinder block. Okay. So while fitting this component, we are expecting perpendicularity between these two surfaces. While assembly, this will get aligned with this surface as well as this surface also. Our bottom surface and this surface also. We are expecting this to be perpendicular. And perpendicularity between axes. So here this axis of bore, axis of cylinder bore should be perpendicular with the top surface. So if it is not perpendicular, then that axis will be inclined and again it will not be assembled with other components. Okay, so a lot of errors may appear due to loss of perpendicularity between this axis and the surface. Okay, so again we will discuss about perpendicularity, feature control frame. Okay, so symbol for perpendicularity is one simple horizontal line and a perpendicular line. Okay, vertical line. So this is symbol for both the cases: perpendicularity between two surfaces and two axes. Sorry, axis and surface. For both the conditions, symbol is same. So this is a feature control frame attached with two perpendicular surfaces. So similar to parallelism, here there is a third chamber mentioning that term feature. Means we are expecting this vertical surface. Here labeling is not applied, but this vertical surface is to be parallel with surface A. So here we are talking in comparative way, means it is compared with this surface. Means with respect to this surface should be parallel. Okay, because here this is a datum. Any one surface can be the datum. Okay, so here we are talking about perpendicularity of this with respect to this. If the feature control frame is attached with this, then this datum identifier will attach with this. Means we are expecting perpendicularity of this surface with respect to this surface. So now regarding feature control frame, now you know what is this characteristic symbol. We'll talk about this second chamber. In second chamber there is a permissible deviation already mentioned, but what about this zone descriptor? Yes, we have to check what is the possible direction of deviation. Okay, so considering possible direction of deviation, we have to mark their symbol. If this deviation is only in one direction, then there is no symbol. If the deviation is generally circular direction, then we have to mention phi symbol. Still, there are two more symbols. Means if deviation is in radial direction, generally arc symbol is also specified. And if the deviation is in two directions, different two directions, then square symbol will be there. Okay. So here we will check what is the direction of deviation. See, we are talking about perpendicularity of this surface with respect to this, because feature control frame is attached with this surface. It is labeled as Q. This one is perpendicularity symbol and permissible deviation is 0.2. Okay, with respect to P. So we are talking about this right angle. Okay, we are expecting perpendicularity between this surface and this surface. Again, what should be the datum? We can consider this as a datum also and this as a datum also. So we have to check convenience of manufacturing, convenience of assembly, or convenience of inspection. Means if it is possible, easy to mount this component on this surface, then we will consider this as a datum and this as a feature under consideration. Okay, so you can consider different operations also. We have suppose actually setting of a component on machine bed is very important. So if object is set on this surface for different operation, no need to disturb this component for machining this. So we will mount this component on this surface and go for this one. This will be the feature under consideration and this will be the datum. Okay, so if you say this should be the datum, then we have to change the setting. Means while machining this surface, we have to hold the component on this surface. Means if this component is circular component, we have to hold this component at this surface. Again, we have to change some settings. So we have to see for manufacturing convenience also. Okay, so as per the manufacturing convenience, it is better if we consider this as a datum. Okay, again, we can apply large surface might be the datum. Means it is not all the time true that large surface is datum, but it's a broader way. You can say large surface can be considered as a datum. So here, just imagine what will be the direction of deviation. So we are expecting this surface to be perpendicular with this one. Means what will be the direction of deviation? So this surface may get deviated in this direction. So this surface may have its orientation like this or like this also. Okay, or it may like this or having some waviness also. Okay, so we can see it in a different drawing. See, these are the different orientation AA and BB. Means this surface might have different orientation with respect to this. Okay, it's not perfectly perpendicular. Perfect right angle is not there, right? So this can be the deviation BB. It may be like this or like this also. So this is the direction of deviation. Only this, right? So that's why it is linear direction of deviation. So no need to mention symbol here. No, okay, no zone descriptor will be here, right? And what is its meaning? Means here the permissible deviation is 0.2 mm. Means the outermost point and innermost point for different deviations. Means suppose this surface is deviated like this AA. Okay. So we have this point 2, which is outermost point, and we have this point 1, which is innermost point. Okay. So distance between this point 1 and point 2 should not be more than point 2, or should not be more than the permissible deviation. Right? Getting so this is how perpendicularity is mentioned. This is the feature control frame and what is meaning of this feature control frame. Okay. Then how to check this? What are the inspecting methods? I think this is very popular method. I think you have seen it with the carpenters also. Okay. So you will find this in inspection room also. So this is called as price square and it is used to check perpendicularity. For carpentry components, we can check it with naked eyes, but for mechanical components, we have to take help of feeler gauges. Okay. So in tri-square also, you will find two different sections, means two different parts. So here at this stage, there will be perfect right angle. Okay, and there is one thin part, but it is having long length, and one thick part having more thickness but very short in length. Okay, so this is called as blare, and this is called as stock. So stock is having large thickness but short length, and blade is having long length and it's thin. So generally, while using this tri-square, stocks are aligned with the atoms. If you want to measure perpendicularity, if you want to check perpendicularity, stock is aligned with the datum and blade is aligned with the feature under consideration, right? So here you can check perpendicularity using tri-square. So here if this surface for this is a workpiece, and for this workpiece this is a datum. So thick part stock is aligned with the datum and thin part is aligned with the feature under consideration. We are checking perpendicularity of this surface with respect to this. So here we can check gap between the blade and the feature under consideration, right? So if we have to align this stock with the datum properly and then check for the gaps available between surface under consideration and blade. So if you want to measure that gap, we can use filler gauges. So about filler gauges we have discussed already. So these are small thin strips of different thicknesses. So you can use these strips to insert in between these gaps and measure that gap. We can use filler gauges in combination also. If you want to check zero point 0.7 mm gap, so we can use zero point 0.5 and zero point 0.2 mm strips combinedly and insert it in the gap. So we can check it. So different strips are available there. So you can use single strip depending on value of the measurement. Okay, how value of the gap. So this is how to check perpendicularity using tri-square. Again, this is very simple and cost-wise very cheap method to check perpendicularity. This is also method where we can use dial gauges and master cylinder. So we want to measure perpendicularity of this surface with respect to some datum P. See, this component is mounted invertedly. Means this is datum feature, datum simulator. Okay, and on this simulator, datum feature is mounted. This is datum feature. So we are measuring perpendicularity with respect to this surface, right? Now we need a support for this dial gauge. So we can take readings on this surface, or if there is any uh, change or deviation in orientation, we will record it in on a dial gauge. But alignment of dial gauge is also important, and you can shift this dial gauge along the height. For that purpose, there should be proper reference, or they should be having some proper perpendicular direction. This direction of movement should be perpendicular properly. For that, we can use master cylinders. So you can see these master cylinders. Okay. So here, the bottom surface and axis of this master cylinder is perfectly perpendicular. Perfectly means maximum as close as possible. These are perpendicular. So we can use master cylinders and V block. So this V block is mounted over this master cylinder to ensure the perfect contact of this circular or cylindrical surface with the V block, and dial gauge is mounted on that. So we'll take different readings at different heights and check the reading at dial gauge. Okay, so maximum and minimum value. Again, same for dial gauge. Every time the process is same. Means difference between maximum reading and minimum reading will be the error in that particular geometrical characteristic. Okay. So using dial gauge also we can check perpendicularity, okay, by shifting this dial and taking different readings. Here this diagram indicates this. We want to ensure contact of this dial gauge pointer or this plunger with this surface. There should be more proper contact. Okay. So to ensure that contact, we can check it by just moving in this circular direction. So where there is a maximum point, there will be the contact. Means in this plunger will get in contact with that maximum point. Okay. So this is one method to inspect perpendicularity. So we have discussed perpendicularity between two surfaces. Now we go for perpendicularity between surface and the axis. Okay. So symbol is same, and this is the requirement. You can check perpendicularity of this pin with respect to this bottom surface. Okay. So perpendicularity of this axis with respect to bottom surface. So here, see, same change is there. For surface to surface perpendicularity, no circular zone descriptor was there. But when we are talking about axis as a feature under consideration, that direction of deviation of this axis is circular. Means we are talking about perpendicularity or squareness of this pin with respect to this bottom surface. So this will have error or tilt in these directions, in this direction or in this direction, or perpendicular to the screen also. So if you are watching this perpendicular to screen also, it may get deviated or it may get tilted. Okay, so tilt can be in all circular directions. Okay, so this axis may get tilted in all the directions around this ideal axis. Okay, so we have to put there pi symbol, circular zone of deviation, right? So now again, generally or maximum times for axis and surface perpendicularity, this surface will be the datum, and this surface or this pin or some cylindrical surface coming out of the surface is a feature under consideration, because it is easy to mount a tri-square on this surface and you can check error with this surface. Okay, so generally bottom surfaces are datums. These are the different conditions we have discussed. Engine block, axis of this should be perpendicular to the surface, or here it is locating pin. So axis of this cylindrical surface or this circular part should be perpendicular to the bottom surface. Means once it is inserted in a fixture plate, it should be fitted properly. Means there should be no change in orientation or tilt should not be there. So to ensure that, it should be perpendicular to this surface. Okay. So these are the different examples: locator pins and cylinder bore axis and upper face. Okay. So this is explanation of perpendicularity or error in perpendicularity. Okay. So this may have tilt in all the directions, right? So here there is a zone descriptor, but that tilt should be within the cylinder of 0.15 diameter. Okay, so 0.15 diameter and 100 height, right? So axis may get tilted like this, like QQ or like PP, whatever may be the deviation, it should be within the cylinder of 0.15 mm diameter and 100 mm height. Okay. If we want to check perpendicularity of hole. Now we have seen this is the pin or some shaft coming out, okay, or some cylindrical surface, cylindrical part is there, and it is perpendicular with respect to this surface, flat surface. But we can apply this case of perpendicularity between axis and surface to the holes also, because we have seen that example of cylinder block where bore axis should be perpendicular to the top surface. So while checking or while in case of such holes, how to check or how to apply perpendicularity of this axis with respect to this surface. So perpendicularity of hole with respect to the surface. It is in this case inspection becomes difficult due to lack of access for many measuring instruments to enter in the hole. Okay, so while checking with the tri-square, if The hole is having large diameter. We can directly use a tri-square. We can put the stock of tri-square here on the flat surface, and blade will be inserted in this cylindrical surface. But it is difficult to check this gap. Means if there is a gap between cylindrical surface and that blade of tri-square, it will be difficult to inspect that, right? Okay, so it is difficult to insert instruments. We cannot insert dial gauges also inside this. So it is difficult. For that, what is the solution? So here if you see this feature control frame, it is different again. One more symbol is added here. Okay, a circle, P symbol enclosed in a circle. This is added in a second chamber after permissible deviation value. So what this P indicates, it's a projected tolerance zone. Because here it is difficult to measure perpendicularity of axis with respect to this surface. What we can do is, we can insert some pin properly fitting inside the hole and of same height, means same in the sense actually this pin should have double height, means hole depth and this projected height should be same. Means if hole is of 25 depth, means pin should be of 50. Means it should get inserted to complete hole, full height of a hole, and same height should be projected out of the hole, right? So height of pin should be 50 and there should be proper fitment inside the hole. See, this is 10G6 and hole dimension is 10H8. So for hole, always H deviation is used, H fitment is used. Okay, and here this F fitment, sorry, G fitment indicates there is a clearance. So fine, very fine clearance. So we have to manufacture such a pin of double the length of hole depth, and diameter should be uh, like with fine fitment, fine clearance. Okay, then it will be like a diameter coming or projected out of hole. So we can use we can treat this like our previous component, means some cylindrical surface or pin with respect to this flat surface. Same situation is now, means when you insert a pin, we can measure with tri-square easily. Okay, and so we can apply here tri-square and we can measure the gap. So that will be the error in perpendicularity. So for holes also, we can use such pins and measure the perpendicularity. But if you are using such pins, or if it is a recommendation from the designer that while checking, while inspecting this, use this pin of 25 projecting outside the hole. So it is mentioned in a feature control frame. Okay. So after maximum permissible deviation, there will be P symbol, and this is the length projecting out, right? So this is projected tolerance zone. Then what are the things to remember in case of perpendicularity? So we have seen perpendicularity between two surfaces, axis and surface. Axis may be of sharp or of hole. Phi is a zone descriptor and it is applicable for the axis type of, means when we are talking about perpendicularity between axis and surface, then phi as a zone descriptor is used, and projected height symbol in case of axis of a hole, right? So these are the things to remember while going for perpendicularity. Now the today's last characteristic is angularity. Okay. So there are different components where we expect some angular dimension or some angle in different faces or in axis and the surface. Okay. So in such cases we can apply angularity characteristic for the component. So we will see these two cases: angularity between two surfaces and angularity between axis and the surface. Actually, perpendicularity is a special case of angularity. Means we can check 90-degree angle with angularity also. But not many components in mechanical engineering are having perpendicular orientation. Means most of the components you will find means they are having 90-degree angle. Okay, so perpendicularity is a separate characteristic, and angularity it is applicable for 0 to sorry means some large value from the 0 and some angle which is less than 90 degree. So angles between 0 to 89, okay, or within 0 to 90. Okay, so for such angles we can apply angularity. Perpendicularity is a special case, means a specific case of angularity. So this is Dowtel guide. So this is used for guides or slideways of different machines. So you will find this slideways for means if you see the milling table of milling machine or table of some different machines. Okay, so one bed means machine bed will slide along these slots or the guides. Means dovetail slot is provided in that bed, and these are called as dovetail guides. Okay. So if you see the assembly is not there, but upper part which will get fitted on this is called as dovetail slot, and which is seen in this image is a dovetail guide. So that part will get fitted on this and it will be slide along this lane. So here at this location we are expecting a proper surface to surface contact, right? So this angle at this location we want to maintain angularity, means that angle should be properly maintained, right, on both the sides. So this is angularity for dovetail slots and dovetail slides also. We can apply angularity. Okay, so here it is same again. You can see this slide. So here it is in contact with this. So here it is called as dovetail slot, and this is dovetail guide. Okay. Now symbol you can see here, symbol for angularity, two angular lines. Okay. Now we'll talk about angularity between two surfaces. So very simple, like you can compare it with the perpendicularity. So only this symbol is changed, this angularity symbol, then the second chamber indicates permissible deviation, then the datum. Okay, so this is the surface under consideration, and this flat surface is considered as a datum. So with respect to this datum feature, this surface should have some angularity tolerance, or it is allowed to get deviated within this limit. Okay, so here one more new condition or new discussion may be there. All the values specified in feature control frame or for all characteristics. Okay, so all these values mentioned in the feature control frame are having mm as a unit. Means here this is 0.03 mm. Okay, but for angularity we are talking about a error in angle. Means we are talking about angular deviation, right? But the tolerance is mentioned in linear dimension. Means this is length in mm, and here we have replaced its tolerance with the linear dimension. So we will see that what is their conversion and how to compare this linear dimension with the angular dimension. Okay. So again, similar way, feature control frame is attached with the surface under consideration and datum feature. This is the datum feature. So again, we will consider dovetail guide here, and we are talking about angularity of this surface with respect to this datum feature A, which is a horizontal surface. Okay, this height is also mentioned here. Now, when we are applying feature control frame, we know these dimensions or basic dimensions, these dimensions are converted to basic dimensions. Means there will be some tolerance for this dimension, there will be some tolerance specified for this angle. All these are considered using this feature control frame. So no need to apply tolerances for these two dimensions. Okay, so these tolerances are taken care by feature control frame. So what is its meaning? Here, this is the possible deviation, PP or QQ. These are the two possible errors or orientations of the surface. Okay, when we consider error or when we consider change in orientation, the angle, if angle is not proper, if angle is not perfectly 60 degree, then change in orientation might be like this, like PP or like QQ. And what is its meaning? Distance between this outermost point and this innermost point, point P and point Q. Okay, this distance should be maximum 0.4 mm because it is mentioned in the feature control frame. Okay, so this should be minimum, sorry, maximum zero point 0.4, or that should be less than zero point 0.4. If it is more than that, then part will be rejected. But as I told you, there is some calculation part because here we have mentioned linear deviation, means error is means a permissible deviation is mentioned in a mm and error will be in angle. First we will see how to inspect this, okay, then we will see how to convert this. Now this is a special instrument to measure angles, so it is available in inspection rooms. It is called as bevel protractor. Okay, and here this is beam and which is attached with the datums. So this will be aligned with the datum, and this one is a blade. So it can rotate around this. See, these are the pins fitted here about at the center, and scales are marked on this circular edge of beam or this component. This is swell pit, dials, okay, and main scale. So we can measure angle using this instrument. So blade is aligned with the component and or feature to be considered, feature under consideration. This blade is aligned with the feature under consideration, and this is aligned with the datum. Okay, so like this we can measure the angle. Okay, so see this beam is aligned with the datum feature, and this blade is aligned with this one. So we can check readings here and we can mark the error in angle. But here using bevel protractor we will get angular deviation in degrees or minutes, degree minutes. Okay, but the value or permissible deviation is mentioned in the mm. Okay, so that is the important part. So such linear deviation is impossible to be detected with bevel protector. So if use the angular deviation detected must be converted to some linear deviation using some expressions. So how to convert this linear angular deviation to linear deviation? Okay. So for our help, these are the conversion values, you can say. 1 degree is 0.0174 radians, and 1 radian is this much degree, 1 minute is equal to this much degree, this much. So this is used for conversion. So we will consider this angle as a 60 degree, ideal angle or expected angle is 60 degree. So using this, we can calculate this length of PP. Using trigonometry, you will have length of PP. Okay, so length of PP is equal to this height multiplied by 1 upon 60. So this is just a trigonometrical calculation. So you can easily do that. Nothing different in this. So this is there is a right angle triangle, and you can take a sine of this angle and you will get the formula. So using that, PP is calculated. PP is 30 of this height multiplied by 1 upon 60. So this answer is 34.64. Okay. So length of PP is 34.64. Now, if this part is manufactured, ideally it should be 60 degree, But after inspection, after checking it with the bevel protector, we find that this angle is 60.36 minutes, means 60 degree and 36 minutes. Means there is an error of 36 minutes. Angle ideally should be the 60 degree. But after inspection, we found that angle is 36, sorry, 60 degrees and 36 minutes. So there is an error of 36 minutes. So what we will do is convert this 36 degree into, sorry, 36 minutes into degree, which is equal to zero point 0.6 degrees. And this degree is again converted to radians. Okay. Okay. We can measure angles in degrees and as well as in radians. Okay. So this minute is converted to degree and degree is converted to radians. 36 minutes is equal to 0.6 degree and which is equal to 0.01047 radians. Okay, because to calculate linear deviation we need angle in radians. So linear deviation is equal to angular deviation multiplied by this length pp. So pp already we have calculated and angular deviation in radians here we have calculated, right? So 0.01047 multiplied by pp. pp already we have 34.64. So with this calculation we will get 0.363. So this is the actual linear deviation. Means after manufacturing this component, okay, and checking it with the bevel protector, what we found is there is a linear deviation of 0.363 mm. So you have to compare this value with the value mentioned in the feature control frame. If it is less than that value or value mentioned in the feature control frame, the part is accepted. If it is more than that, part is rejected. Okay. So this is the value linear deviation actually, and it can be compared with the permissible deviation, right? Permissible deviation means which is mentioned in the feature control frame. So here, same thing, 0.363 is less than, means if it is less than or equal to zero point 0.4, then part is accepted, right? So again that comparison is given, means permissible deviation 4, means you can do reverse calculations also. Means what is permissible deviation specified in feature control frame is 0.4 mm. So convert that 0.4 mm into angular deviation in degrees. Using same formula, you can get that value. Okay. So linear deviation mentioned in a feature control frame can be converted to degrees. So directly you can compare readings with the bevel protector with this value 0.66 degrees. So if actual readings is less than 0.66 degrees, then it's okay. Okay, the part is accepted. So this is about calculation for the angular deviation and linear deviation. Like this, we can do inspections for angularity. Now, one last case we will discuss angularity between axis and surface. Axis and surface. Very common example. So this is the axis, and we are expecting its angularity with the base surface. Okay. So this is angularity symbol, permissible deviation, and the datum. Right. I think here there is a mistake in this image. Here we are talking about angularity of this uh, axis. So this axis may get deviated in any direction. Okay. So in this direction also or in this direction also. Right. So we are expecting here circular zone descriptor. Phi symbol should be there. Okay. Actually, if you see it properly, if this axis get deviated or tilted in this direction, then only there is error in angularity. So there is only one direction of deviation. If you want to speak here, actually, if you see, there is only one direction of deviation. Means there should be linear direction of deviation. But If you see in assembly point of view, if you try to assemble any pin or any cylindrical component inside this, if it is deviated in this direction, perpendicular to the screen, then also there will be difficulty for fitment, right? So it is okay if you mention linear deviation, but for proper fitment, some people may expect circular zone also. Means some designer can say ask for a circular deviation, circular zone also, because it is axis and this may get deviate in other directions also. So that is also considered as an error. That's why it is better if you maintain circular zone. Otherwise, uh, if you see properly, means if you see uh, a deviation, direction of deviation, here there is only one direction of deviation, which will affect the angle actually. Okay? But for safer side, we are maintaining circular zone descriptor. Just understand the difference. Okay. You can see this dipstick holes in engines. Okay, lubricant are filled, means engines are filled with lubricants. So to pour this lubricants, or there is some dipstick. Dipstick is there to check the oil level inside the uh, engine or some gearboxes. Okay, so these holes are having some angle. You can check it with your vehicles. Means for two wheelers or for four wheelers also you will find some dipstick, and which is at angular position. Okay, having some angle with respect to bottom surface or the mounting surface. So there we can apply this angularity condition. You can see this. So this is the bottom feature. With respect to this, we are expecting angularity of this axis. So again, how to check this? Means if it is a outer diameter, then we can use bevel protector to check the angle of this pin or the cylindrical surface. But here it is hole. So how to check it? Again, we can use projected tolerance zone. So we can insert a pin here and measure angle of this pin. So we can mark the error in angle with the bevel protector. We can attach this bevel protector with this cylinder or with this pin and get the actual deviation, right? So this is similar to perpendicularity. That's why I am not explaining more. You can get it easily. Okay. See here there is a phi symbol. Okay, try to understand this concept. Means, actually speaking, this is only one direction of deviation. So there should not be any circular zone, or it should be linear. But safer side, this axis may get deviate in any direction. That's why we have mentioned phi as a circular zone. So some people may say that there is no requirement of phi symbol. They are also correct, but we have to check for the object. Means if it is really required, then if object asks for the circular zone, or designer can apply this. Okay. So safer side, phi is better. So what is to be remembered? Two conditions. Angularity can be applied to two surfaces, axis and surface. So phi as a zone descriptor is there for axis conditions and projected height symbol, similar to perpendicularity between axis and a surface. Okay, so this is about orientation type of characteristics, parallelism, perpendicularity, and angularity. Okay, just revise all this. Till now we have finished 7 characteristics. Okay, 8 I think. Position already finished. Okay, so I think how many remaining? 5 or 6. 6 characteristics are remaining. Runout, 2 runouts, 2 profiles, and symmetry and concentricity. So we'll try to finish all these 6 characteristics tomorrow. Okay, very simple characteristics. Only 10-15 minutes required for each characteristic. Okay. Yes. If anyone wants to ask any query, please.
Does anyone have questions? Kindly ask. Post your queries so that we can ask the questions. Also, all have to solve the quiz from time to time. So only you will get the certificate.
Quiz, I
After
think
has
only three or four quiz are there. Uh, One
yes.
more I will post today because considerable
Okay.
part
This
of
will be quiz
engineering.
number 4, na sir?
Yes, I think there is quiz on day one. Day two and three, there is one single quiz. Day four and five, there is
Okay.
one quiz. Now it's a
Yes.
seventh day, I think. So on
Yes.
sixth and seventh,
Yes.
there will be one quiz. So today I will post one.
Yes. So
Yes,
all total are 4 quizzes. All should solve
right,
and
okay,
submit it.
right. Yes, sir. Thank you all.
Okay, sir. Thank
We
you.
will meet tomorrow.
Yes.
Okay.